Hey, this is Horner, and this is your introduction to uniform circular motion, or how the world rotates, or how the world turns. An object can move at uniform speed in a circle of constant radius, so we call that uniform circular motion. We want to know, why is that an accelerated motion if it's traveling at a uniform speed? So notice here we have uniform speed and a constant radius. So our speed is constant, but something must be changing, and the thing that's changing here is our direction. So whenever you have a direction change, then we have something called a change in velocity. So if you think about it, if something's going in a circle, and if the velocity is the same all the way around, so let's just say that the velocity has the same magnitude, so we're making all our arrows the same length. Notice though that the direction changes, so that would definitely be an acceleration. For the next part, centrifugal force is a myth. It doesn't really exist. So we need to go back to Newton's laws and really look at those to see why that feeling you get on merry-go-round is so weird, or that one that you get in a turning car. It feels like it's pushing you out, when actually it's not. It's actually pulling you in. So when a car accelerates, when you're a passenger, you feel like you're kind of flung backward. Your inertia really is just resisting the acceleration, and you're not really flung backward. Your body just wants to stay there while the car goes forward, and that gives you the illusion that you're being pushed back into the seat. When a car slows down, you feel like you're flung forward. And that's really not happening. It's just that you are trying to keep going, and your body is resisting that negative acceleration. Your body really just wants to keep going as that car slows down and accelerates backwards. When you make a left-hand turn, so notice that we're moving to the right, your body feels like it's getting pushed out to the side. So it feels like it's getting pushed out, when in actuality your body is just trying to stay straight and the car is making a turn in this direction. So you're actually getting pushed towards the center, and that's what we call a center-seeking force, or a centripetal force. So like I said, you feel like you're flung to the outside, but in reality your body simply wants to keep moving in that straight line. So as a general rule, whenever you feel like you're trying to be flung in a certain direction, the acceleration is actually pointing in that absolutely in the opposite direction. So if you remember about all the elevator problems, when you feel like you're flying up, the acceleration of the elevator is actually down, and when you're sinking down, the acceleration is usually up. So the acceleration in uniform circular motion, that velocity vector at any given point is subjected to an acceleration that turns it, but does not speed it up or slow it down. So we saw that acceleration vector is always at right angles to the velocity, and it points to the center of the circle. So the acceleration is responsible for uniform circular motion. We call that centripetal acceleration. So you'll notice that I'm always moving tangent to this circle. So it doesn't matter what point I'm at, you'll see that my velocity is moving tangent, but my acceleration is at a 90-degree angle to that, and it is always pointing towards the center of the circle. So we call that centripetal acceleration. The equation that we use for centripetal acceleration is just v squared over r, where v is the tangential speed in meters per second, and r is that radius that we have in meters. Centripetal acceleration, like we've said time and time again here, always does point towards the center of a circle. So how about force? A force responsible for uniform circular motion is what we call centripetal force, and it simply is just mass times centripetal acceleration. So just F is equal to MAC. If we plug in that v squared over r for that AC, we get FC, or centripetal force, is mv squared over r. And that force is also always towards the center of the circle. Centripetal force is not unique. It actually arises from other forces, and so the centripetal force, we won't draw it on a diagram. We actually will show all the forces that are making it happen. Friction can be the can make centripetal force work. So as a car is making a turn, the force of friction acting on those turn wheels will provide a centripetal force required for that circular motion. If you take a bucket of water and you tie it to a string and you swirl it around your head, the force of tension in the rope is making that can keep pulling towards the center, so that's the centripetal force. And then gravity also acts as a centripetal force. So as the moon orbits the Earth, that force of gravity acts on the moon by pulling it towards the Earth, and it ends up moving in a circle. If I have an automobile on a bank curve, and you're going to see some problems that deal with this, it also uses the normal force to provide that necessary centripetal force. The weight on a string moving in a vertical circle, we'll do a lab like this. So I can't remember what this is called. It was called a ball and chain on a stick. But the centripetal force, it's a mace, I guess is what it's really called. So here the centripetal force arises from both the combination of tension and from gravity. So something a little bit heavier spinning around your head. If you go to Dollywood and you ride on the Tennessee Tornado, the centripetal force when you're upside down arises from a combination of both the normal force and of gravity, and that's what you feel. Centripetal force can do no work, so it doesn't do any work at all. It alters the direction without altering the speed. Since all the energy remains constant, then we say that the work is zero, so it really does no work at all. We've seen this equation before. This is just the universal law of gravity, where we have a couple of different masses and they do interact. It could be you and the person sitting next to you. You wouldn't really feel anything because it's so very small. But if I have a really big planet like the Earth, then I do feel something in terms of gravity between me and the Earth. Acceleration due to gravity, if I want to solve for that, I can find G. And G here is just equal to universal gravitational constant times the mass of the Earth all over the radius squared. How did I get that? Well, I said that mass times gravity is weight, and then we also know Fg is equal to this equation, so I've crossed off my m's, and then I rearranged the equation for G, so I just kind of left G where it is. So if I get rid of the m's, you'll notice that this resulting equation is the same thing as this. So if I want to know what the value is for G for any object, all I need to know is the radius of the object and the approximate mass of that object. So this is how you could find it out very quickly for Saturn or for the moon or for almost any object by just using this equation. So that's kind of cool. In fact, if we look at acceleration and distance, we can see the acceleration of gravity as I get further and further from the Earth tends to go down. And you'll notice that this shape of this curve is an inverse curve. This is really an inverse square relationship. So it's not just 1 over, it's actually 1 over that squared. So that's the deal there. Next thing is just some different radius and masses of different planets, and then you can see what their G value is for each one. It's interesting that Uranus is very close to 9.8 for Earth, and so is Venus. But Jupiter would crush you. That would not be very much fun. And then Pluto, poor little Pluto is no longer a planet, but Pluto would be so light that you could jump pretty far if you were on it. The very last thing that I want to show you is the period of a satellite. So if you're orbiting something, we can find out the time it takes to go around in one time in seconds by using this equation, where if I know the orbital velocity, I can just say that's equal to 2 pi times the radius, or the distance between the center of two objects, and we can divide that by the time. So if I want to know the period, I just take 2 times pi times the radius all over my velocity, and when I do that, I'm going to end up with period. And that is your introduction into central net force or circular motion.